Hello, this is Dr. Dueñez from UT San Antonio. In this section, we'll be talking about ElGamal digital signatures and the digital signature algorithm, DSA, which is what is behind the digital signature standard, DSS, and that is closely related to ElGamal signatures. So stay tuned through this fairly long lesson. So let me remind you that we've already met the ElGamal crypto system in its most classical setting, in which we are essentially relying on the difficulty of the discrete logarithm problem uh, in residue rings Z modulo n. So various crypto systems, various systems based on the difficulty of the discrete logarithm problem are named after ElGamal. So today we're talking about ElGamal framework for digital signatures. We're also going to be working in residue rings. So let's get started here. Um, and here, so take a large prime number P, and we're actually going to be working in the modulo P. So remember that because P is prime, the multiplicative group of units modulo P, meaning Z mod P with the exception of the zero element of Z mod P, forms a group under multiplication, and that group is cyclic of order P minus 1. So you are deleting 0, you're left with P minus 1 elements, which form an abelian group, but that group is cyclic. So the concept, then we have what is a primitive root, G. You can consider G to be an integer whose powers modulo P exhaust all of Z modulo P, except of course for the zero element of Z modulo P. So these, this prime P and this primitive root G are public parameters in the ElGamal digital signature scheme. Now we get to the secrets. So the signer's Samantha's secret is an integer A that I guess you can take this as a random integer between 1 and P minus 1. So you can think about it as something that is going to be used as an exponent, and exponents in the group of units modulo P are defined modulo P minus 1. So using this secret exponent of the signers, little a, you raise the primitive root G to the power of A, and you obtain this element capital A, which is public and is actually the verification key. So we have little a is an exponent and it is secret. Big A is an element of Z mod P, and it is public. Right. So those are the ingredients for ElGamal digital signatures. So in this signature scheme, what we call a document, our documents, they are actually going to be, you can think of them as integers modulo P. So that's the things that we're going to assign. And what is the signature of D? Just as the case was for ElGamal crypto system, there is a random input to the signatures. In particular, you can see from this that signatures are not going to be unique given a document. They're hard to produce, unfeasible to forge. I'm sorry, they're hard to produce. They're hard to produce if you don't have, of course, the signing key, right? But they're not unique. So a document typically has a lot of valid signatures, right? So you choose a random element which you think of as a random exponent. That's going to be a random exponent. So you can think about it as, and it has to be coprime to P minus 1. So remember that exponents are really elements defined modulo p minus 1. The random exponent has to be coprime to p minus 1. That is a requirement because we, in signing a document, are going to have to invert k modulo p minus 1. So the signature consists of two pieces. The first one, as promised, we're using this random exponent as an exponent of the generator g. So g to the k, of course, with arithmetic modulo p, that element S1, which we can think of as between 1 and p, is the first ingredient. So the second one is a little puzzling at first. The second one is obtained as follows. So you take the multiplicative inverse of k, of the random exponent, which exists because k is coprime to p, and this is going to happen modulo p minus 1. That is an important distinction. So you take that inverse exponent, and then you take the minus a times s1. Now, the thing here, and this is really weird the first time you see it, is that we're taking documents that we think of as modulo p, but we must identify the document with an integer, say in the range from 1 through p, because otherwise d doesn't really directly make sense as an element modulo p. So we actually have to identify d with a bona fide integer. The exponent a we have been thinking of as an element modulo p minus 1, but this S1, which was born as an element modulo p, right? But it's coprime to p, so it can be identified, is represented by the class of an element between 1 and p, but not equal to p. So we can convert it into an integer in the range 1 through p minus 1, and therefore identify with a class modulo p minus 1. So all of this requires identifying d certainly and s1 with actual integers less than p. So that's a feature of the signature. There is what is known here as a non-homomorphic identification between elements of z mod p and z mod p minus 1. Since p is a huge prime, it doesn't make much of a difference from a computational perspective. But algebraically, the fact that we're rather arbitrarily choosing to represent things modulo p with integers in the range from 1 through p makes a big difference from an algebraic point of view. And as I said here, k inverse is the inverse of k modulo p minus 1. And the signature of the document D consists of the pair S1 and S2. So how does verification work for ElGamal? How do we check if the signature consisting of the two pieces S1 and S2 is valid for the document D? The verification algorithm is the following. You check modulo P, whether G raised to the power of the document D is congruent to the verification key A raised to S1 times S1 raised to the S2. As you can see, all of this involves only public information, the verification key capital A, the secret signing key little a is nowhere to be seen here. And of course, if this congruence holds modulo P, then we accept the signature. Otherwise, we reject it. Why is this verification process sound? Let's check that when S1 it actually comes and S2 both actually come from the correct procedure that was used to generate them by the signer, then this test here will pass. So what happens is that, well, what is a to the s1 is 1 to the s2. Let's start on the right-hand side, right? So a, remember that a, the verification key capital A is g to the little a. So this here is g to the little a s1. And s1 is simply g to the k, as you may remember, right? So this is g to the ks2. So now we just have a very innocuous multiplication of two powers of the generator g. This second k times s2, remember that exponents are defined modulo p minus 1. So the fact that k is coprime to p minus 1 and it has a multiplicative inverse k inverse working in arithmetic modulo p minus 1, which is the exponent's live, is important because this congruence here, which is the one that defines S2, is equivalent to passing k to the other side. K times S2 is d minus a s1. So ks2 that appears here becomes d minus a s1, correct? And then simply by laws of exponents, this is really literally equal to g to the d. So when the signature is valid, the verification congruence is satisfied modulo p. So now we get to an important question, which is, you may think that maybe forging ElGamal signatures is easy or relatively easy because after all, a document has many possible valid signatures because of that random exponent k, correct? Um, so different random k will give different signatures, and many different signatures are valid for the same document. And in fact, so long as you give x a value x for x1 and y for s2 that satisfy the verification condition for ElGamal, g to the d is congruent to capital A to the x times x to the y modulo p, with x and y in the correct range 1 through p minus 1, then you have a valid signature for d. So forging signatures for ElGamal amounts to finding solutions xy to this weird congruence. And it's particularly weird because x is both an exponent and a base. And that's why this weird non-algebraic play between considering the same integer x as something modulo p minus 1 when it plays as an exponent and as something modulo p when it's on the base is just weird. So this equation is not very algebraic in some ways. And solving it or finding solutions of it given a document D is what is involved in finding signatures for D. Now, as I mentioned earlier, ElGamal systems are, their security depends on the difficulty of finding discrete logarithms in whatever group we're working in. So if you look at this equation, which is the equation that must be satisfied for signature x comma y to be valid for document D, this is all happening in the group UP, which is all, the non-zero elements modulo P. And if you want to rewrite it in terms of discrete logarithms to see the connection, right? So by taking discrete logarithms to the base g, where g is our chosen generator, so the discrete logarithm here is d, and that has to be, by properties of discrete logarithms, that would have to be congruent to x times the discrete logarithm of capital A, the public key, plus y times the discrete logarithm of x. But this is a congruence happening modulo p minus 1, which is where the exponents live. So we've traded a congruence modulo p, which is algebraic, I suppose, to a congruence modulo p minus 1, which involves discrete logarithms. Of course, it goes without saying that if you well, in this case, or the adversary, you and your role as adversary, you as evil Eve, you can take discrete logarithms base G in the group UP. Then you can certainly forge signatures. For instance, you could do this by finding, right? This is like the conspicuously hardest part here. If you could find the discrete logarithm of the public verification key, big A, you would be finding the signing secret exponent little a, right? And then you could proceed to sign just exactly in the same that sum does. So, which roughly speaking, you choose a random x, and then I'm sorry, you find a random value for the log of x, so that's our k. Then this is g to the k, and you find whatever y is necessary to make this hold. And that's already the reason why this congruence always has a solution. Once you put in an x whose logarithm is equal to k, co-prime to p minus 1, there's always a unique solution for y, and that solution is easy to find in a computationally effective manner. That has everything to do with the fact that this is the exponent little k, which is co-prime to p minus 1. So you can, when it's a coefficient, you can divide by that coefficient. So, however, I mean, so being able to find discrete logarithms certainly breaks ElGamal systems, such as this signature system. But it's conceivable that because this is the equation we need to solve, to find solutions to, that it is conceivable that there may be a way to find solutions without actually literally being able to take discrete logarithms. And so that's what forging ElGamal signatures boils down to: finding solutions to this congruence by any means necessary, whether you use discrete logarithms or not. I guess the way we like to do this, let's just do a practical example, numerical example. So consider a moderate size prime, p equals 7,919. Then it turns out that 7, g equals 7 is a primitive root modulo p, in other words, a generator. And let's consider the secret signing exponent of Samantha's to be little a equals 314. Every mathematician's favorite secret. And therefore, the public verification key, capital A, is obtained by raising 7 to the 314 modulo p. So you get 7,144. That's the verification key. Consider document D equals 2020. May make people think of a specific year. And I'm just going to take a random element, k equals 4321, whatever. This, you have to check that this is co-prime to p minus 1, but it is. So it's random, but it has to satisfy that condition, right? And then it's easy to find the multiplicative inverse modulo p minus 1 of k is 689, so their product is congruent to 1 modulo p. So the signature has the two ingredients S1, obtained by raising 7, g equals 7 to the exponent 4321, and that gives 7542 modulo p. And the second piece is literally d 2020 minus 314 times 7542 multiplied by 689, and you reduce this modulo p minus 1 to find 2694. And the verification checks out. If you take the values above, a to the s1, s1 to the s2, and g to the d, both of them are 6724 modulo p. So it's a valid signature, it passes the test. Okay, so now on to the second part of this lecture on the digital signature algorithm. So this is a variation, of ElGamal. The basic idea is that if you remember in ElGamal, we were working with a cyclic group of large order p minus 1, where p is prime, which was a group of units modulo p, right? But the condition of choosing elements that are coprime to p minus 1, those are the random exponents, k. So that's a little cumbersome, right? Because p minus 1 has, it's a composite number, so it's even in particular. So you have to be worrying about generating exponents that have coprimality conditions, and you may need to try more than once. Also, because of the existence of algorithms that reduce the discrete logarithm problem to discrete logarithms and prime order groups, in many ways, the security of ElGamal crypto system depends on the largest prime q dividing p minus 1. So the first thing that DSA does is simply choose at the outset to work in a prime order group, right? So the setup here is just like before, a large prime P, but there's a second prime Q, which you should choose to be a large prime, which is a divisor of P minus 1. And we're going to be exclusively working in a group of order Q. So another public ingredient of DSA is an element G, but that element G has order equal to a prime Q in modulo P, right? What is going to be private, just as before, is a secret exponent. But unlike the case of ElGamal, the secret exponent is going to be an exponent for G, which has order Q. And for that reason, the secret exponent should be, between 1 and Q. Obviously, exponent equal to Q is really bad because G to the Q is equal to 1. So I guess we can decide that the exponent is in the range from 1 to Q minus 1. But it's really an exponent that is defined modulo Q. You should think of little a as an element of Z modulo Q. And the documents to sign are going to be integers in the range also from 1 to Q minus 1. And they're also going to be exponents. So we're going to use them as exponents. Now, just as in ElGamal, there is a random ingredient to DSA signatures. So we need to choose a random exponent, let's say in the range from 1 to Q minus 1. So it is going to be used as an exponent of G. And well, here is where we reap one of the benefits of working in a group of prime order Q, is that since we are restricting K to not be divisible by Q and Q is prime, then automatically K has a multiplicative inverse modulo Q. I'm going to be consistently writing modulo P in red and modulo Q in green, as you can see. Now the signature consists of two parts, as before. So the first part of the signature is obtained by raising G to the power of K. This is naturally defined as an element modulo P, correct? So this is an integer like between 1 and P minus 1. But now we're going to take the remainder of that modulo Q. So we end up with an element that is, between 0 and Q minus 1. So ultimately, the security here it depends on the size of Q, as you can see. The second part of the signature is also very similar to the case of ElGamal. The second part of the signature also is defined modulo Q, and it comes from doing D plus A times S1 multiplied by the multiplicative inverse K inverse of K modulo Q, right? So those are the two pieces of the DSA signature. Now the verification of a purported or a presented signature S1 and S2 for document D is obtained also with two preliminary steps. So there's two partial verification pieces, V1 and V2. The first one is simply D divided by S2 modulo Q. And the second one is S1 divided by S2 modulo Q. And now the verification itself takes the form of this equation is G to the V1 multiplied by capital A to the V2 modulo P. Now reduce modulo Q the same as S1, which remember also S1 was, in the generation of the signature, should have been something modulo P modulo Q. So this is actually not terribly surprising that you had this mod P mod Q given the way that S1 had been defined. If this is actually true, right, these two are integers between 1 and Q. If they are the same, accept the signature. Otherwise, reject it. So the proof of soundness of DSA, I'm going to do that in two parts. First, we're going to be working exclusively modulo P. So remember that there's this double mod P mod Q issue. So the first part is just working modulo P. So G to the V1, let's start with G to the V1 times A to the V2. So if you do the calculation here, remember that V1 is DS2 inverse modulo Q. Remember that green means modulo Q. And V2 is AS1 over S2 modulo Q. So G to the V1 becomes G to the D over S2. And A to the V2, the public A is G to the A. And V2 is S1 over S2. So we get this. This is a congruence modulo P. It's a red congruence. Why? Because at the level of exponents, this is at the level of powers of G. So and the exponents are congruent modulo Q, which is what they should be in order to get congruences modulo P once you take the power, correct? So again, when exponents are taken modulo Q, the respective powers of G to those exponents are congruent modulo P, which is what this red means here. Now continuing, I'm just going to use the laws of exponents here. To combine the product of these two powers as G raised to the power D plus AS1 divide the whole thing divided by S2. But remember that S2 is defined as D plus AS1 divided by K. So this is modulo Q. So K times S2 is D plus AS1, correct? And that means that if you divide D plus AS1 by S2 in Z modulo Q, the answer is K. So this quantity here is congruent to K modulo Q, which is what should be at the level of exponents, so that the powers of G end up being the same modulo P. So we have this congruence, G to the V1, A to the V2 is congruent to G to the K modulo P, right? So that's just what we showed, that these two are the same number. And therefore, when you take these numbers as between 1 and P and you reduce them modulo Q, right? So what you get is that this quantity modulo Q is equal to this quantity modulo Q, but this quantity GK mod P mod Q is exactly what we call S1. So it follows that S1 is actually equal to GV1 AV2 mod P mod Q, and therefore DSA checks out, and it is a sound encryption system. I'm sorry, a sound signature system. So let's do a numerical example of DSA signatures. I'm going to take this prime P, 7,927, then P minus 1 is 2 times 3 times a fairly large prime, 1,321. So I'm going to take this to be Q, which divides P minus 1. And it turns out, just by chance, that G equals 2, that as taken as a base, it actually has order equal to 1321 in Z mod P. I'm gonna take my secret signing key little a as 2718. Not very secret. Mathematicians like 2718 dot dot dot. So that's my secret. And then my public verification key becomes G raised to the power of A, capital A, and that is 4986, again working modulo P, right? The document I'm going to sign is 999, and my random exponent is 1234. I couldn't have taken 1234 when we're doing ElGamal because 1234 is even and P minus 1 is even. So this is not co-prime to P minus 1, but it is co-prime to Q. See? Right. Now next we generate the signature proper. Remember that S1 is G to the K. So 2 to the 1, 2, 3, 4. And this is done in arithmetic modulo P. Right? So we get 765, just so happens. And S2, we're going to take our document, 999, plus our secret, 2718, times the S1 that we just computed above, and divide by K. So we'll multiply by the multiplicative inverse of 1, 2, 3, 4. I really should say that, right? But since we're working modulo Q and Q is a prime, this is okay. I can write division. And if you do this modulo Q, you get 869. So that those two pieces, 765 and 869, constitute the DSA signature of the document 999. Okay, so now remember the verification. First, we find two pieces modulo Q. The first one is V1, obtained as the document divided by S2. And when you do this modulo Q, you get 556. So 999 divided by 861 is 556 modulo Q. And the second part, the second V2 that we need before we pass to the verification proper is also a modulo Q ingredient. This is obtained as S1 divided by S2, or 765 divided by S69, which in Z mod Q comes out to 878. Now, now let's figure out what G to the V1, A to the V2 is modulo P. First, just doing arithmetic modulo P, right? So this is 2 to the 556 by 4986, 878. So you get 7370 mod P. Now, we are going to have to compare this to S1, but when we do arithmetic modulo Q. So this piece, which GV1 AV2 modulo P is 7370. If we now take that modulo Q, that's 7370 modulo Q, and we get 765, which is the same as our S1. So the DSA signature checks out, and that's the end of today's lesson.